Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students, so we begin our new discussion. But it's a continuation of the chapters around modern physics. In some ways, now but it's not exactly modern physics. The transistor was invented by Bardeen. First there was Shockley, who worked with semiconductors, and he received a Nobel Prize. Then there was Bardeen, who also received a Nobel Prize for the discovery of the semiconductor-based transistor. There were earlier versions of this called the diode and the triode, and then there were these semiconductor-based versions of the same, and so there is a history around these things. Not exactly a history, but there is, there was an earlier version and a later version. There's a 2.0, and so we look at some of these things today. Okay, so I hope you can see my screen. So let me. So I have shared my screen, and so now. Okay, so. So let's let's get going here. Okay, so so firstly, let me introduce to you Sushruta for NEET, which is our flagship NEET platform. Sushruta is a trademark of JnanaMarga Technologies. So you go to the Google Store and then you look for com.jnanamarga.sushruta and you can download. It is easily the most affordable and best app, which contains now videos, textbook, slides, and importantly, the assessment. So we have all four integrated into one app, and it's the most affordable platform you can buy. Then for students who are looking at JEE, we have our flagship Ramanujan platform. Our platform was built with significant help from teams which are based out of IIT Chennai, and so it's now available. You can get it, download it, and then you can go from there. So today we are going to be looking at insulators. Actually, today it's all about semiconductors. Okay? Now we've already seen insulator, material which doesn't allow electric charge movement, right? So how does electric charge move? It's through the motion of electrons from a region of higher potential to a region of lower potential, right? So now you have a conductor, even if the conductor is like, it's a wire, right? So let me show you a standard wire, right? See, this is a standard wire. Inside it, there is a conductor, right? Outside it, there's an insulator. So when I touch it, I don't feel any charge because the outside plastic is made of an insulator. Inside, you see the metal. That is a conductor. So that inside, there's typically copper that is used as the most powerful conductor. So insulators and conductors, I bet you we've already discussed this, right? So we use electric wires inside. Now, there is a special type of material which becomes a conductor under certain circumstances, and it is not a conductor under other circumstances. Such a device is called a semiconductor. So it's sometimes this and sometimes that, sometimes a conductor, sometimes an insulator. That's why it is always called a semiconductor. We use them for so many different operations, most of all to make the chips that go in your computer. Okay, so it is a extremely important material. I live in Silicon Valley. Silicon is a semiconductor and it is typically doped. Okay, so conduction is due to the working of a conductor. Okay, conduction became possible, but in insulator, electrons are closely packed and required very high amount of energy that is impossible to provide. The electrons in an atom are arranged in discrete energy levels. Often they are termed 1s2, 2s2, p, 1s2, 2s2, 2p6, 3s2, 3p6, right, etc. Right. So they are what are called discrete energy levels. We already looked at this when we looked at the Bohr atom, right? Now each energy level has a quantum of state, right? And so typically, if you say 1s2, right, it means that 1s level can have at most 2 electrons. The 2 refers to 2 electrons. 2s2 also has only 2 electrons. Then there is this 2p6 which can have up to 6 electrons. And so in normal conditions, electrons start filling the quantum levels from the lowest energy level. In solids, the outer electrons interact significantly with the neighbors and then they shift the energy levels of quantum states. Okay, so that is the key thing. Okay, so they can more easily move around. Okay, now that's why they become conductors. Now the lowest energy band is called the conduction band, like which is not completely filled. Okay, if there is a energy level which does not, where all the electrons are not filled, that is called the conduction band. Okay, this is due to the electronic structure only. Now the energy band just below the conduction band, the fully filled band below the conduction band, is called the valence band. Okay, now electrons in valence band correspond to those strongly bonded to the atoms, whereas electrons in the conduction band correspond to weakly bounded atoms. So if you have a conductor, those are the ones that flow. Okay, the conduction band is partly filled. We say the material tends to be a conductor. Now the energy band structure in solids may be classified into 4 broad types. You have the conductor A, the conductor B, right? So here the conduction band is filled, the valence band is filled and then the conduction band is partially filled. Here the valence band is mostly filled. Okay, conduction band has some loose electrons. Now the insulator, the valence band is filled and the conduction band is empty. Okay, and then in a semiconductor, there is some amount of flow between the two. Okay, electrons in valence band correspond to those strongly bonded to the atoms, whereas electrons conduction band weakly bound. Conduction band is partially empty, right? The material is a conductor. Conduction band is completely empty. It may then be either an insulator or a semiconductor. So note this point. Conduction band is completely empty. Insulator, the band gap is small, say less than 3 eV. The material is semiconductor. The band gap is large, say more than 3 eV. Material is a insulator. Because of thermal interaction, some electrons can go from valence band to conduction band, leaving empty quantum states in the valence band. If an electric field is applied to a semiconductor, conduction can take place to the electrons promoted to the conduction band, also due to the electrons in the valence band shifting to fill the empty quantum states. So that's the most important thing here. This is the most important idea that you're going to learn that is new, right? So if there is an electric field applied to a semiconductor, conduction can take place. Okay, to the electrons being promoted to the conduction band, also to the electrons in the valence band shifting to fill the entire empty state. So that's the most important line I want you to remember. So now let me stop sharing this, then we will bring the next set of slides. Okay, so but remember that all right. So now there are let's quickly go over the revision again, right? For an isolated atom, possible energy states are discrete. We talk about 1s2, 2s2, 2p6, 3s2, 3p6, right? Having different energy levels. For a gas slash vapor, the same energies are available. Number of quantum states increases according to the number of uh, uh, protons or the number of electrons. Electrons fill the orbital. So if you have 8 electrons, it will do 1s2 first, then it will do 2s2, then it will go to 2p6, etc. Okay. So if you have 8 electrons, 1s2 will be filled, 2s2 will be filled, 4 in 2p6. Okay. The last non-empty level may be completely or partially filled. When it's completely filled, that's when you start having this new thing called the semiconductor. Okay. Now, when it is partially filled, when the last is partially filled, it is what is called the conduction band. The material is typically a conductor. Now, as the atoms are brought closer to form the solid crystalline state, outer electrons also start interacting through bonding. So, in a crystal, you have electron here, proton here, what is that? Nucleus here, nucleus here, nucleus here, nucleus here, nucleus here, nucleus here, and then they are all in this kind of this formation. And then there are these electrons which are completely enclosed and held inside this each but then they can also be shared in the presence of a electric field. So that's the basic idea there. The lower energy levels are populated by electrons and not affected, right? But the higher ones, they tend to be shared a little bit between the various nuclei. Good conductors, the conduction band is partially filled. Enough electrons in empty state, even at low temperature, so they will flow. In insulators, the conduction band will be completely empty, and the energy gap between the valence and the conduction band will be large. So when that happens, there's not the ability to push the electrons out of the captive, from being the captive audience of the atom, of the nucleus. In semiconductors, the conduction band is completely empty at very low temperatures, but the energy gap is small. And so, for instance, in silicon, it is 1.12 electron volts. Silicon is the most important of the semiconductor materials. That's why I told you I live in Silicon Valley. Here, all the semiconductors were made initially by this company called Fairchild Semiconductor, followed by, and from Fairchild, I think Fairchild started with Shockley, I forget, but from Fairchild, there emerged another company called Intel. And this is a Dell PC that I'm working on. Right here it says Intel inside, Core i5, V Pro. So this PC has Intel in it. And Intel was the second company in semiconductors, and they are very famous for the work they did, and they continue to do, almost 50 years old, okay, or 55 years old. At higher temperatures, say at room temperature, some of the electrons, the valence band, get sufficient energy from thermal interaction to cross over the gap and occupy quantum states in the conduction band. This leaves behind vacant states in the valence band. So the conduction band is completely empty at low temperatures, high temperatures. Some of the valence electrons get transported to the conduction band. So intrinsic semiconductors are semiconductors like silicon and germanium. Okay? In semiconductors, before using, we have to dope the semiconductor with some impurities. So we try to make a bond with other atoms that can, so it can free an electron or hole for conduction. So that's how it happens. There are a few electrons, there are a few impurities which then introduce a few free electrons. Typically, those impurities are of two types. They are called N impurities and they are called P impurities. N impurities have a negative, N for negative and P for positive. P means they will, have a hole, and N means they will have a spare electron. They'll have a free electron, and P means they will have a hole. So the impurity you introduce will make it either a N or a P. The impurity will be some kind of, phosphorus or some kind of aluminum, some kind of material, which then, adds you an N type or a P type. Okay. So normally they will be, these silicon has 4 electrons in its final orbit, 4e. Okay? In outer shell will have 4e. So it will form very nice bonds. So, but then what happens is that when you introduce a 3 or when you introduce a 5, then you will have the corresponding doping that happens. Now we say that we call these extrinsic. So it is as doped or is an extrinsic semiconductor. So now the N-type semiconductor will have a majority of E charge carriers, while a P-type conductor will have a majority of holes. It will have a space for something. So because of the presence of these things, under a voltage or under an electric field, there will be a flow. Okay. So now here is a grid of silicon atoms with a impurity in phosphorus. Now the phosphorus introduced a trivalent impurity is added. There's a lack of one electron in impurity element, so a hole or vacancy is there. That's how we proceed for semiconductors with an impurity doped into it are called extrinsic semiconductor. So 45 shows a schematic representation of intrinsic and extrinsic. All right, so there you go. So these trivalent impurity doped semiconductors are p-type semiconductors. Charge carriers are holes. Doping control on conductivity. Pentavalent impurities. Intrinsic semiconductor, Ne is the number of electrons, Nh is the number of holes. Ne equals Nh equals Ni. Okay, so that is these trivalent impurity doped semiconductors are p-type semiconductors. Okay, and so they have a hole. Charge carriers are holes. Now a pentavalent impurity, on the other hand, is an N-type semiconductor. So they will have more extra electrons. So the majority of the carriers are not holes, but they are electrons. Therefore, they will have loose electrons, which can then be transported under a electric field. Okay, so that's the basic idea behind these two types of elements. So now Now so now let's look at the revision. So the PN junction, right? Now, what is a PN junction? The conductors of a semiconductor can be precisely controlled by doping an element with less or more valency. So, for instance, if you have silicon and you dope it with a pentavalent impurity such as phosphorus, right, which makes conduction of electron concentration much higher than the hole concentration. So, if there's phosphorus, the five valent, right? Now, if you at the same time, you can also have what are called N-type semiconductors. These are N-type semiconductors, and so they are what are called donors because they donate a electron. Okay? Now, these donors, impurities, are created slightly below the conduction band occupied by the extra electrons attached to the impurity. Due to thermal energies, large number of them go to the conduction band, increasing NE. Intrinsic concentration is of the order of 10 to the power of 10 per cm cube. The impurity electrons for parts per million type doping could be around 10 to the power of 6. Increasing number of electron concentration enhances the rate of recombination of electrons, holes, the hole concentration further reduced. For silicon, doping a trivalent impurity such as boron makes the hole concentration much higher than conduction electron. These are called P-type semiconductors. Impurities are acceptors. So you have N-types which are donors and P-types which are acceptors. So now P-type, the impurity is typically phosphorus. N-type, the impurity is typically aluminum or something similar. So now the valence electrons can jump to these impurity levels, making holes in the valence band, therefore increasing the NH, which is the number of holes. Intrinsic concentration, we are of 10 to the power of 10 per cm cube. But the hole concentration can be around 10 to the power of 16 per cm cubed. So now Ne times NH equals Ni squared. So rate of recombination of electrons and holes and the electron concentration further reduces. Thus, conduction electron concentration or hole concentration changes due to doping. The average charge density remains zero in the material. This is because only neutral atoms are doped. Okay, so remember that. So typically there is a band, right? We discussed the band in the case of the semiconductors. Now, when an electric field is applied to the semiconductor, the electrons and holes move systematically. The current is generated. The sum of the two currents, IH plus IE, will give you the total I. This is proportional to the concentration of the two charge carriers, the holes and the electrons. So now let us introduce this, what is called a PN junction. So now the bottom you have silicon, right? The bottom is entirely silicon doped with an N-type material like phosphorus. Okay? Then in that we then put a P-type material. They dope on top of that, where there is a substrate which is N-type, and they have a P-type material. What is a P-type material? Aluminum. They dope this part with aluminum, this part with phosphorus. So aluminum and phosphorus. So now you have a N-type semiconductor, a P-type semiconductor joined together, and then on top of it, they put some metal. So now the metal, then there's metal below too. There's metal at the top, metal contact at the top, right? Then there's metal below too. So now when you apply a voltage between here and here, right? What happens? When you apply a voltage between this metal contact and this metal contact, something happens. The N-type has electrons as charge carriers. The P-type has holes. The doping is done in silicon. Then recombination of holes and electrons take place. Electron drift towards holes, hole drift towards. Due to recombination, meaning holes and electron pair neutralize. Depletion layer is formed after recombination. So now this is the basic idea. H. It's an E, and an H. Therefore, you have a P-type and an N-type, with a depletion layer in between. Okay, so that's what's happening here. In between these two here, right? You have that depletion layer. So that depletion layer, one side is N, other side is P. So you'll have a negative and a positive layer in between, just like your capacitor, right? Just like there, where there is a displacement current. This is also a little bit similar, but not exactly, in some ways. So there's a electric field between the E and the H. There's a plus side here, the minus side here. Therefore, you then have the electrons drift towards holes, and a drift current is produced, which flows in opposite direction. And so the electrons flow this way, the current goes that way, as you know. Now, due to the depletion layer, there are differences in voltage or potential of two layers. There exists a barrier voltage or the depletion layer. So, we apply a voltage higher than the barrier voltage, PN junction will be working. So, with that, I'm going to stop for today a little bit early, with a view that you will take some time to understand this material, read your textbook. Okay, this material you must understand it in great detail. What is what is conduction band? What is valence band? What is doping? What is p-type material? What is n-type material? And what is how are these p-n junctions made? Okay, so you get this much. This is a very basic understanding of this material, and so my aim is not to cover too many slides too quickly, so you don't get any of it, but at least make sure that you get this material, so you relate it to your drift current, etc., displacement current, and then drift current, right? You have conduction current, IC, displacement current. Now you have drift current. Drift current goes in the opposite direction, the flow of electrons. So this is somewhere in between. It is not a insulator, which is what you will typically have in a capacitor, right? It is not a conductor, is what you will have in a metal, right? This is in between. Okay, this is a semiconductor. So the behavior is slightly different between both the conductor and the insulator. You must understand how it works. How previously we had this dielectric in a capacitor. Then we had the conductor with loose electrons, being able to flow, right? Like when you have a lot of electrons in the conduction band, there's free electron flow, right? Copper. Now this is different. This is a semiconductor. Doping, the p-type doping and n-type doping. When you apply a voltage, what happens? So you look at that. You look at when it's direct bias, when it's reverse biased, and the corresponding things that happen in terms of how and when there is a current that flows. What kind of currents flow? Okay. So all these things will come into play. Firstly, in the context of a PN junction, then you will have this other thing called a transistor, which has an NPN or a PNP. Then we will look at all these ideas, and then we will take things forward as we look at these various types of conductors, semiconductors. So there are two types of semiconductors, but we will look at all that in the next class. But my advice to you is to read the chapter very well and very, very carefully. Once you understand the chapter, then this material, we can build it more easily. Okay. So with that, I'm going to stop for today. I'm going to really recommend that you spend some time reading the chapter before you look at the next lecture. Let's say you're seeing it much after I've conducted my lectures, then this is how you should go about it. Read the material now so that you get a little bit of a get ahead with the things. Therefore, when you re-explain this material, continue the material, you will have a very good understanding. Right. So with that, I'm going to stop, and then we will continue again next class. So until then, I hope you all have a wonderful week ahead, and then we will meet